Hello there, and welcome to Science into Sleep. Tonight, we are going to rest beneath the widest sky there is. Not the sky above your roof, but the one that holds everything. The Milky Way. This is our galaxy. A slow spiraling structure of hundreds of billions of stars. So vast that light itself needs 100,000 years just to cross from one side to the other. And yet, for all its enormity, it is home. Every star you have ever seen with your own eyes lives here. Every sunrise, every moonrise, every familiar constellation belongs to this one quiet neighborhood of the universe. Tonight, we will wander through it gently, from the ancient stars that circle its halo to the glowing clouds where new suns are still being born, and discover why the galaxy we live in is one of the most calming, most quietly extraordinary places in all of existence. If you enjoy these gentle journeys, I would be grateful if you liked, subscribed, or left a quiet thought in the comments. It helps other weary wanderers find their way here. But right now, none of that needs your attention. Just settle in. Let your muscles soften. Let each breath arrive without effort. And allow your mind to loosen its hold on the day. Now, let's begin. The Milky Way is the galaxy that holds everything you have ever known. Every person who has ever lived, every ocean, every mountain, every rainstorm, and every quiet evening. All of it exists within one single structure of stars. A vast, turning spiral drifting through space in absolute silence. And on a clear, dark night, far from the glow of towns and highways, you can see it for yourself. A pale band of light stretches from one edge of the sky to the other, soft and luminous, cutting across the darkness like a river made of something finer than water. Ancient peoples gave this glow many names. To some, it was a celestial road traveled by spirits. To others, it was a stream of milk spilled by the gods. And from that image, the name we still use was born. In nearly every culture, that quiet arc of light inspired wonder, because it was beautiful and because it was constant. Always there, regardless of season, regardless of century. It asked nothing. It simply shone. The band is not uniform. In certain directions it glows more brightly, swelling with a dense, warm luminosity, particularly toward the constellation Sagittarius, where you are looking toward the galactic center, through the thickest concentration of stars and dust. In other directions, it narrows and dims, tracing a more delicate path through the sky. And threaded through the brightest stretches are dark lanes, regions where thick clouds of interstellar dust block the light of the stars behind them, creating rifts and shadows within the glow. These are not empty spaces. They are some of the most materially rich regions of the galaxy, where gas and dust are dense enough to give birth to new stars. On summer nights in the northern hemisphere, the Milky Way arches high and bright, passing through Sagittarius and Scorpius near the horizon and climbing through Cygnus overhead. In winter, it traces a fainter path through Orion and Gemini. The view changes with the seasons because our planet tilts and turns, presenting different stretches of the galactic plane to our eyes as the year unfolds. Yet the galaxy itself does not change. It simply waits, offering a different angle of the same vast structure each time we look up. What you are actually seeing when you gaze at that band is the galaxy itself, viewed from the inside. Our solar system sits within the flat disk of the Milky Way, and when you look along that disk's plane, you are peering through the greatest concentration of stars billions of them, stacked so deep along your line of sight that their individual lights blend together into one continuous glow. Turn your eyes away from the band, perpendicular to the plane, and you peer through far fewer stars into the darker, quieter space above and below the disk. The shape of the night sky, in other words, is a map of our galaxy's structure. The bright band is the disk seen edge-on from within. The darker regions are the directions where the galaxy thins, and the universe beyond begins to show through. This was not always understood. For most of human history, the band of light was a mystery, its nature debated, its composition unknown. It was Galileo, in the early 1600s, who first turned a telescope toward it and discovered that the glow was made of countless individual stars. Far too many and far too faint to resolve with the naked eye, but unmistakably there. That single observation cracked open the door to a new understanding. The Milky Way was not a smear of celestial paint. It was a structure made of suns. The Milky Way is what astronomers call a barred spiral galaxy. That means it has a flat, rotating disk of stars with sweeping spiral arms curving outward from the center. And running through its core is a long, dense bar of older stars that gives the inner region an elongated shape rather than a simple round bulge. It is not a perfect pinwheel. No real galaxy ever is. The arms are broad, somewhat ragged, and they wind outward with varying degrees of tightness. The bar introduces an asymmetry that a simpler spiral would lack, steering gas and stars along preferred paths near the center. If you could travel far enough away to look back at the Milky Way from above, you would see something like a vast, slowly turning Catherine wheel, bright arms spiraling outward from a glowing core, the whole structure embedded in a much larger, fainter cloud of old stars and unseen mass. But no one has ever taken that photograph, and no one ever will from any human spacecraft in any foreseeable future. Every image you have seen of the Milky Way as a complete spiral, those beautiful overhead views in textbooks and documentaries, is either an artist's illustration, a composite model built from data, or a photograph of another galaxy that resembles ours. We've never seen our own galaxy from the outside. Everything we know about its shape has been painstakingly pieced together from within. The way astronomers accomplished this is a story of patience stretching across centuries. In visible light, much of the galaxy is hidden behind thick curtains of interstellar dust, microscopic grains of carbon and silicates that absorb and scatter starlight with extraordinary efficiency. You cannot simply point an optical telescope toward the center of the Milky Way and see what lies there. The dust blocks the view so thoroughly that entire regions of the galaxy are invisible at optical wavelengths. But radio waves pass through dust almost freely, and infrared light can slip through where visible light cannot. By surveying the sky at these longer wavelengths, astronomers began to trace the distribution of hydrogen gas throughout the galaxy, and the spiral structure that visible light observations alone could never reveal slowly came into view. One of the most important tools in this effort was the 21-centimeter emission line of neutral hydrogen. Hydrogen is the most abundant element in the galaxy, and it radiates at a precise radio frequency that can be detected across enormous distances. By measuring how that signal shifts in frequency due to the motion of the gas, a technique rooted in the same principle that makes a siren change pitch as it passes you, astronomers could determine not only where the gas was, but how fast and in which direction it was moving. Those measurements allowed them to construct maps of the galaxy's gas distribution, revealing arm-like structures that matched what spiral galaxies look like from the outside. Later, infrared surveys mapped the positions of millions of stars that dust had rendered invisible in ordinary light, and the picture sharpened further. In more recent decades, the Gaia Space Observatory has measured the precise positions, distances, and motions of well over 1 billion individual stars, giving astronomers a three-dimensional view of the local galactic neighborhood more detailed than anything that came before. All of it assembled from the inside by observers who have never stepped beyond their own small corner of the disk. It is something like drawing a map of an entire city while standing in one room, using only the sounds and vibrations that reach you through the walls. And yet, the map has turned out to be remarkably good. The understanding that our galaxy has a definite shape and a measurable size came in stages. In the late 1700s, William Herschel attempted to map the Milky Way by counting stars in different directions, reasoning that more stars in a given line of sight meant the galaxy extended farther that way. His method was limited. He could not see through the dust that hides much of the galaxy. But it established the principle that the Milky Way could be studied as a physical structure with real boundaries and a real geometry. More than a century later, Harlow Shapley studied the distribution of globular clusters, those ancient swarms of stars that orbit the galaxy in its halo, and realized that they were not centered on our position, but on a point far away in the direction of Sagittarius. That meant the Sun was not at the center of the galaxy, as many had assumed, but out toward the edge. It was a quiet shift in perspective, moving humanity not only from the center of the solar system, but from the center of its own galaxy. From Herschel's star counts to Shapley's globular clusters, to the radio maps and satellite surveys of our own era, the story of mapping the Milky Way has been a story of gradual revelation, each generation seeing a little further, a little more clearly, into the structure that surrounds us all. At the heart of the Milky Way lies a dense, luminous concentration of stars, known as the galactic bulge. This is a rounded, slightly boxy region that swells above and below the plane of the disk, packed with stars far more tightly than they are packed out where we live. Many of the stars in the bulge are old and reddish, their brightest days behind them. And they move on orbits that are more varied and less orderly than the nearly circular paths followed by stars in the outer disk. The bulge is not a separate object. It blends continuously into the disk and into the bar that runs through it. But it represents a region where the galaxy's history is written in denser script, where old stellar populations dominate, and where the gravitational forces shaping stellar orbits are at their most complex. Running through and beyond this bulge is the central bar, a structure estimated to span roughly 25,000 light-years, composed primarily of older stars whose orbits have been shaped by the galaxy's gravitational field into an elongated, coherent pattern. The bar is not a solid beam. It is a gravitational phenomenon, a region where the combined pull of millions of stars channels their motion into a shape that rotates as a unit. Bars like this are common in spiral galaxies. Perhaps 2/3 of all spirals possess one, and they play an active role in a galaxy's evolution, funneling gas inward and influencing how and where new stars form near the center. The Milky Way's bar was not easy to detect because we are embedded in the disk and looking through it at a shallow angle. But infrared surveys revealed its presence by tracing the telltale distribution of old red giant stars whose collective light maps the bar's outline across the inner galaxy. Extending outward from this central region, the spiral arms wind through the disk like slow, curving rivers of light and gas. The Milky Way possesses several major arms: the Perseus arm, the Scutum Centaurus arm, the Carina Sagittarius arm, and others, along with smaller spurs and branches that weave and connect between them. These arms are not rigid structures bolted into place. Stars do not remain locked within a given arm for their entire lives. Instead, the arms are best understood as density waves, regions where stars, gas, and dust are temporarily compressed as they orbit the galactic center. The idea is similar to a slow-moving cluster of traffic on a highway, where cars enter the congestion, bunch together, and then gradually move through and out the other side, even as new cars enter behind them. The material moves through the pattern, but the pattern itself persists, rotating at its own steady pace. This is why spiral arms remain visible in galaxies that are billions of years old. They're not winding up and tangling into themselves, because they are not composed of the same material forever. As gas enters an arm and is compressed, it collapses into new stars, and the brightest of those new stars, the hot blue massive ones that shine most fiercely, light up the arm like beacons before burning out relatively quickly. Meanwhile, older, dimmer stars drift through the arm and continue onward, their contribution to the arm's glow modest in comparison. The spiral arms shine so prominently because they are where star formation is concentrated, and star formation, by its very nature, produces the most luminous stars the galaxy can offer. Our own solar system sits in one of the galaxy's more modest structures, a region called the Orion Arm, sometimes referred to as the local arm or the Orion Spur. It is a smaller arm nestled between the larger Perseus arm on one side and the Carina Sagittarius arm on the other. For a long time, it was treated as a minor spur rather than a true arm, but more recent observations suggest it is more substantial than originally thought, a significant structure in its own right, even if not quite as grand as the galaxy's primary arms. Our Sun sits roughly in the middle of this feature, about 26,000 light-years from the galactic center, which places us approximately halfway between the center and the outer edge of the disk. It is not the most dramatic neighborhood in the galaxy. It is not the densest, the brightest, or the most active. By galactic standards, our stretch of the disk is relatively calm, removed from the intense radiation and crowded stellar traffic near the center, and removed from the sparse, thinning outskirts where the disk fades into halo. This quietness is worth pausing on. In busier regions, supernovae explode more frequently, stellar encounters are more common, and the radiation environment is more intense. Out here, in this sheltered corridor between larger arms, conditions have remained stable enough for a small, rocky planet to hold liquid water on its surface for more than 4 billion years. Whether our galactic position actively contributed to the emergence and survival of life remains an open question. but the thought itself is a gentle one. Of all the places we might have found ourselves, we are in a soft and steady corner. Our neighborhood is quiet in another sense as well, one that has only recently come into focus. The solar system sits inside a vast cavity in the interstellar medium, known as the local bubble, a region roughly 1,000 light-years across, in which the density of gas and dust is far lower than the galactic average. This bubble was not always here. It was carved gradually by a series of supernova explosions that occurred roughly 10 to 20 million years ago, in a nearby association of young, massive stars. When those stars reached the ends of their lives and detonated, their blast waves swept outward, heating the surrounding gas to millions of degrees and pushing it away from the center of the explosion. Over time, successive blasts hollowed out a large, roughly spherical cavity, its walls compressed into dense shells of gas and dust that now surround us on all sides. Inside this cleared-out space, the view is remarkably transparent. There is less interstellar material between us and the nearest stars than there would be in a typical stretch of the galactic disk. And that relative clarity is part of the reason our local sky is as rich and detailed as it appears to be. The walls of the local bubble are not passive boundaries. They are sites of ongoing activity. Where the swept-up gas has piled into dense shells, new molecular clouds have begun to form. And within some of those clouds, new stars are igniting. The very explosions that cleared our neighborhood also compressed material at the edges into conditions favorable for star birth. In a sense, the bubble is both a monument to stellar death and a nursery for the next generation. Several of the nearest star-forming regions, including parts of the clouds in Taurus, Scorpius, and Ophiuchus, sit along or near the bubble's walls, their existence owing something to the ancient blasts that shaped the cavity we now inhabit. The Scorpius-Centaurus Stellar Association, the nearest collection of young, massive stars to the Sun, lies along one edge of the bubble and may have contributed some of the later explosions that helped define its current shape. We live, in other words, inside a structure that was created by dying stars and that is now giving rise to new ones along its margins. It is a pocket of calm surrounded by a rim of quiet creation, a clearing in the galactic forest made by fire, slowly regrowing at the edges. And inside it, undisturbed, our small world has orbited steadily for millions of years, sheltered without knowing it, resting in a space that ancient explosions made safe. The stars you see on any given clear night are mostly your nearest neighbors within this arm. Sirius, the brightest star in the night sky, lies a mere 8.5 light-years away. Vega, Altair, Betelgeuse. Each of these familiar names belongs to a star that shares our local stretch of the galaxy, orbiting in roughly the same direction, at roughly the same distance from the galactic center. They are companions in the most literal sense, fellow travelers on a shared arc through the disk. The disk itself, where the spiral arms and most of the galaxy's gas reside, is a layered structure. Astronomers describe it as having two main components, a thin disk and a thick disk. The thin disk is where most of the visible action takes place. It is roughly 1,000 light-years thick from top to bottom, and it contains the youngest stars, the densest clouds of gas and dust, and the regions where new stars are still being born. This is the layer you see, when you trace the bright band of the Milky Way across the sky. The thick disk extends farther above and below the midplane, perhaps 3,000 to 4,000 light-years in total, and it is populated by older stars, moving on wider, more inclined orbits. These stars were likely born earlier in the galaxy's history, when the disk was less settled, or they were scattered outward into higher orbits by gravitational disturbances over billions of years. The thick disk is quieter and more diffuse. Its stars are dimmer and more spread out. But together, the thin disk and the thick disk form the flat, extended plane that gives the Milky Way its characteristic shape and produces that luminous stripe we see overhead on dark nights. Every grain of dust in that band, every faint star lost in the glow, is a fellow traveler in this immense, turning disk. The disk, for all its apparent flatness, is not perfectly level. If you could see the entire Milky Way from the outside and look at it edge on, you would notice that the outer edges bend gently away from the midplane, curving upward on one side and downward on the other, like the brim of a hat that has been softly folded. This warping of the galactic disk has been known for decades, detected through radio observations of hydrogen gas that extends well beyond the visible stellar disk, but its cause has been a subject of ongoing investigation. One leading explanation involves the gravitational influence of the Milky Way's satellite galaxies, particularly the Magellanic Clouds, whose combined mass and orbital motion tug on the outer disk and excite a slow, oscillating distortion that ripples outward from the inner regions. The warp is not static. Recent observations suggest it is precessing, rotating around the galaxy's center over time like a wobble passing through a spinning top, which means the shape of the outer disk is subtly changing even now, bending and flexing in response to forces that operate across tens of thousands of light years. Alongside the warp, the outer disk also flares, meaning it grows thicker with increasing distance from the center. Near the Sun, the thin disk is modest in its thickness, but in the galaxy's outskirts, that thickness can double or even triple as stars and gas spread into a wider vertical range. The flare reflects a gradual weakening of the gravitational forces that keep the disk thin near the center. Farther from the dense core, the restoring pull that holds stars close to the midplane is gentler, and their orbits can wander more freely above and below. The result is a disk that puffs outward as it extends, like a sheet of dough that is thin in the middle and thicker at the edges. These features, the warp and the flare, are reminders that the Milky Way is not a rigid geometric object. It is a living structure, responsive to the gravitational nudges of its companions and to the distribution of mass within itself. Its edges breathe. Its plane is not fixed. Even the shape of the galaxy is something that continues to evolve, adjusting itself in slow, gentle motions that no single lifetime could ever detect, but that the patient work of observation has revealed, ripple by quiet ripple. Beyond the disk, extending in every direction, like a vast spherical envelope, lies the galactic halo. This is a region far less crowded than the disk, populated by scattered old stars and by globular clusters. Dense ancient gatherings of hundreds of thousands of stars, each one a tightly bound city of suns orbiting the galaxy like slow satellites. The halo stars are among the oldest in the Milky Way, and their chemistry reflects the early universe. They contain very few of the heavier elements that later generations of stars would forge in their cores and scatter into space through explosions and stellar winds. In a sense, halo stars are fossils. They formed when the galaxy was young, when the raw materials available were almost entirely hydrogen and helium, with only the faintest trace of anything heavier. Some of them have been shining for nearly as long as the universe has existed. The globular clusters that share the halo are similarly ancient, tight, glittering swarms of stars that have survived for billions of years, orbiting the galaxy on long, looping paths that carry them far above and below the disk. These clusters are found throughout the halo, and each one is a self-contained relic of the galaxy's deep past. Their stars were born together, and they have remained together across cosmic time, bound by their shared gravity into compact spheres of light that predate most of the structures in the disk. When you observe a globular cluster through a telescope, you are looking at something that was already old when the sun first ignited. The halo itself extends for hundreds of thousands of light years beyond the visible edge of the disk, far larger than the bright spiral it surrounds. It is a quiet, dim region, but it carries profound importance. The motions of halo stars and clusters provide some of the clearest evidence that the galaxy is embedded in an enormous envelope of dark matter, invisible mass whose gravitational influence shapes the Milky Way at the grandest scales. But that thread will unfold in its own time, and it will be waiting when we arrive. The scale of all of this can be difficult to hold in the mind, and that may be precisely why it is so soothing. The disk of the galaxy spans somewhere between 100,000 and 200,000 light years across, depending on how the measurement is made and where the boundary is drawn. A single light year is the distance that light, traveling at roughly 300,000 kilometers every second, covers in an entire year, approximately 9.5 trillion kilometers. The galaxy, then, is unimaginably wide. The number of stars it contains is similarly uncertain. Estimates range from roughly 200 billion to perhaps 400 billion, and that range is not vagueness. It is honesty. Many stars are too faint, too small, or too buried in dust to count directly. Our census remains incomplete, and there is something peaceful in that openness. The galaxy is too large and too rich for any single survey to capture all of it at once. We know enough to understand its shape, its rhythms, its general character. And we know enough to know that there's more to learn. When ancient astronomers first counted the visible stars, they numbered a few thousand at most. That is all the unaided human eye can see on even the clearest night. Behind each of those visible points lies an uncounted multitude, too faint for our eyes, but shining steadily nonetheless. The galaxy is crowded with light we cannot perceive. Even with the most powerful telescopes, we are catching only a portion of what is there, because distance and dust conspire to hide the rest. The Milky Way reveals itself slowly, in layers, and each layer seems to contain more than the last. The nearest star beyond our own sun is Proxima Centauri, a faint red dwarf that lies about 4.25 light years away. Even at the speed of light, the fastest speed the universe permits, you would need more than 4 years to reach it, traveling every second without pause. At the speeds our spacecraft actually achieve, the trip would take tens of thousands of years. And that is just the nearest neighbor, the closest other sun in a galaxy of hundreds of billions. The center of the Milky Way lies roughly 26,000 light-years from where we are. The far edge of the disk stretches tens of thousands of light-years beyond that. To cross the entire galaxy at the speed of light would require well over 100,000 years. These are distances that gently undo the grip of ordinary worry. They do not diminish your life. They do not make it less real. They place it in a context so vast that urgency itself begins to soften, the way a candle flame softens in the presence of the morning sky. Whatever is weighing on your mind tonight is real, and it matters. But it is happening on a small, warm world, in a quiet arm of a galaxy so enormous that your entire lifetime is less than a flicker in its long, slow turning. Our sun is one star among those hundreds of billions. It is not particularly large. It is not particularly bright. It is a yellow dwarf, middle-aged by stellar standards, roughly 4.5 billion years old, with perhaps another 5 billion years of steady burning ahead of it. It sits in the disk, orbiting the galactic center, along with all its neighbors, at a distance that places it in the calm middle ground between the crowded core and the thinning edge. It is an ordinary star, and around this one ordinary star, on one small world, something looked up, noticed the pale band of light overhead, and began to wonder what it was. There is something both humbling and deeply reassuring about that. We did not need to be at the center. We did not need a spectacular star or a privileged vantage point. We are where we are, in a modest arm circling an average sun, and from here, with patience and curiosity and the slow accumulation of knowledge across generations, we mapped the shape of the galaxy that carries us. The Milky Way is not an object somewhere else in the sky. It is the sky. It is the context in which every star, every constellation, every planet you have ever seen exists. When you watch Orion rise in winter or trace the arc of the summer triangle overhead, you are looking at neighbors within the same galactic structure. Every sunrise is powered by a star that orbits the same center as all the rest. Every meteor that streaks across your window is a grain of dust drifting through the same disk. The galaxy is not distant. It is immediate, beneath you, around you, above you, so close and so all-encompassing that most of the time you do not notice it at all. You are wrapped inside it, the way you are wrapped inside the atmosphere, unable to step outside and see the whole, yet entirely dependent on its presence. And perhaps that is the most restful realization of all. Home does not always announce itself. Sometimes it simply holds you quietly, while everything else falls away. The disk turns. The arms wind slowly onward. The old stars in the halo keep their ancient orbits, tracing paths they have followed since before the Earth existed. And somewhere inside all of it, on a world so small, it would vanish from any galactic map. You are here, breathing slowly, resting gently, held by a structure older and wider than anything the mind can fully contain. There is no edge you need to reach tonight. There is no destination beyond the one you are already in. From our quiet arm, the Milky Way stretches inward. If you could follow that stretch, crossing thousands of light years of open space, drifting past long avenues of stars and slowly thickening curtains of dust, the galaxy would change around you. It would grow brighter. It would grow more crowded. Stars that were once separated by comfortable distances would press closer and closer together, their combined light filling the sky with a glow that never quite fades. And the dust that lightly scatters starlight in our neighborhood would deepen into something far more substantial, a barrier so thick that visible light from the galactic center cannot pass through it at all. Behind that barrier lies the most extraordinary region of the Milky Way, a place where millions of stars crowd into volumes so compact that the sky seen from within them would blaze with an almost unbroken sheet of light, a place where gas spirals inward at tremendous speeds, where magnetic fields trace vast luminous threads through space, and where a single invisible object, more massive than 4 million suns, sits in near-perfect stillness at the heart of everything. This is the ancient center of our galaxy. And despite being the most extreme environment within it, there is something deeply calm about what we find there. The center lies in the direction of the constellation Sagittarius, hidden from our eyes by lane after lane of interstellar dust. This dust is not the kind you brush from a shelf. It is composed of microscopic grains, carbon, silicates, and other compounds, each one far smaller than a human cell, but collectively so abundant and so efficient at absorbing light that they render the galactic core invisible at optical wavelengths. For every photon of visible light that sets out from the center in our direction, the overwhelming majority is absorbed or scattered before it reaches us. The center of the Milky Way is the brightest, most densely populated region of the galaxy, and yet for most of human history, no one could see it. It was there all along, hidden behind a curtain that no eye could penetrate. The brightest swell of the Milky Way's band in the summer sky marks the direction of this hidden center, and the dark rifts that run through it are the very dust clouds that block the view. When ancient observers looked toward Sagittarius and saw that glowing complexity threaded with shadow, they were looking at the doorstep of the galactic core without knowing what lay beyond. The first crack in the curtain came from an unexpected direction. In 1932, a young engineer named Carl Jansky was working at Bell Telephone Laboratories in New Jersey, investigating sources of radio static that interfered with transatlantic voice communications. He built a large rotating antenna mounted on a set of wheels from a dismantled automobile and began systematically cataloging the different types of noise it picked up. He found 3 categories. 2 were straightforward, local thunderstorms and distant ones. The third was a persistent, faint hiss that did not seem to come from any earthly source. Over months of careful observation, Jansky noticed that the hiss followed a cycle slightly shorter than 24 hours, matching the rotation of the celestial sphere rather than the sun's apparent motion across the sky. The signal was strongest when his antenna pointed toward the constellation Sagittarius, toward the center of the Milky Way. What Jansky had detected was the galaxy's own radio emission. Radio waves generated by charged particles spiraling through the galaxy's magnetic fields, passing through dust that would have stopped visible light completely. His discovery, published modestly in a paper and briefly noted in the press, did not receive the attention it deserved at the time. But it opened a door that would eventually transform our understanding of the galaxy. Radio waves moved through interstellar dust as freely as sound moves through fog. What was opaque to the eye was transparent to the radio telescope, and the hidden center of the Milky Way was suddenly within reach. In the decades that followed, radio astronomy grew from a curiosity into a powerful discipline. Larger and more sensitive radio telescopes were built, and with each advance, the galactic center came into sharper focus. Astronomers discovered intense radio sources near the center, compact, powerful emitters of radio energy that hinted at extreme physical processes unfolding in the inner galaxy. Alongside radio, infrared astronomy developed as another way to peer through the dust. Infrared light, with its longer wavelengths, slips through interstellar grains far more easily than visible light does, and infrared surveys began to reveal the individual stars packed into the central regions. Millions of them glowing through the haze like lanterns seen through a dense forest. X-ray telescopes launched above the atmosphere on rockets and satellites added yet another layer, detecting the high-energy signatures of superheated gas and violent encounters that neither radio nor infrared could capture on their own. Each wavelength told a different part of the story, like voices in a choir singing different harmonies of the same piece. And together, these observations built a portrait of the galactic center that is both magnificent and strangely ordered. Despite holding the most extreme conditions in the Milky Way, the center is not a place of chaos. It is layered, structured, and governed by forces that have maintained a kind of equilibrium across billions of years. The innermost region of the galaxy is anchored by a dense concentration of stars known as the nuclear star cluster. Within just a few light years of the very center, stars are packed so tightly that their density is estimated to be millions of times greater than the density of stars in our neighborhood around the sun. If you could somehow stand on a planet orbiting one of these stars, the night sky would be radically unlike anything we experience on Earth. There would be no true darkness. Thousands upon thousands of stars would crowd every direction, many close enough that their combined light would wash the sky with a soft, continuous glow, bright enough to read by, bright enough to cast faint shadows even in the dead of night. The familiar feeling of stars scattered across a dark canvas would be replaced by something closer to a luminous ceiling, an overwhelming abundance of light from every angle. And yet, despite this extraordinary crowding, individual collisions between stars remain remarkably rare, even in the most densely packed regions of the galaxy. The distances between stars are still immense compared to the sizes of the stars themselves. Two stars in the nuclear cluster may be separated by only a fraction of a light year, but a light year is still trillions of kilometers. Space, even crowded space, retains its vastness. There is room between the lights. Many of the stars in this central cluster are old, red giants and other evolved types that have been circling the galactic center for billions of years. Their light is warm and reddish, their brightest days long behind them, and they trace orbits shaped by the deep gravitational well of the inner galaxy. But among them are younger, hotter, massive stars, blue and luminous, whose presence has puzzled astronomers for decades. These young stars should not, by the usual understanding of how stars form, be where they are. Star formation requires cold, dense clouds of molecular gas that can collapse under their own gravity. contracting and heating until nuclear fusion ignites in their cores. Near the galactic center, the conditions work against this process at almost every step. The gravitational tides are immense. The pull from the enormous central mass is so strong that it stretches and shears gas clouds apart before they can condense into the dense knots from which stars are born. The radiation environment is harsh, the turbulence is extreme, and the temperatures are elevated well above the levels found in the quieter star-forming regions of the outer disk. And yet, there the young stars are, luminous, massive, apparently thriving in a region that should have prevented their creation. Several explanations have been proposed. Perhaps these stars formed farther from the center and migrated inward over time, their orbits gradually decaying through gravitational interactions. Perhaps clouds of gas near the center occasionally achieve densities extreme enough to overcome the tidal disruption, collapsing rapidly into stars under conditions that exist nowhere else in the galaxy. The answer is still being investigated, and the debate is one of the more engaging puzzles in galactic astronomy. What the presence of these young stars tells us, regardless of how they came to be, is that the galactic center is not simply a vault of ancient relics. It is still producing new stars, still creating, even in the most forbidding environment the Milky Way has to offer. At the very heart of all of this sits Sagittarius A star. This is the supermassive black hole at the center of the Milky Way, an object whose mass is approximately 4 million times the mass of our Sun, compressed into a region of space smaller than the orbit of Mercury. It does not shine in any conventional sense. A black hole, by definition, possesses an event horizon, a boundary beyond which nothing, not even light itself, can escape the pull of gravity. No signal leaves from within, no photon climbs back out. And yet the presence of Sagittarius A star is known with extraordinary precision, not because it emits light, but because of the effect it has on everything that surrounds it. The evidence is written in the orbits of stars. Beginning in the early 1990s, 2 independent teams of astronomers undertook one of the most painstaking observational campaigns in the history of the science. Their goal was to track the motions of individual stars in the immediate vicinity of the galactic center, year after year, and to use those motions to infer the mass of whatever unseen object they were orbiting. One team, led by Reinhard Gansel at the Max Planck Institute in Germany, used the European Southern Observatory's telescopes in Chile. The other, led by Andrea Ghez at the University of California, used the Keck Observatory in Hawaii. Both teams observed at infrared wavelengths, which can pierce the dust that blocks visible light, and both employed adaptive optics, a technology that corrects for the distortions caused by Earth's turbulent atmosphere, to achieve the extraordinary resolution needed to pick out individual stars in the dense, crowded field near the center. What they were attempting had never been done before. The galactic center is far away, thickly obscured, and fiercely crowded. Resolving individual stars in that environment required not only the best telescopes on Earth, but a level of patience measured in decades. Over the course of those decades, both teams watched the stars move, and what they found was breathtaking in its clarity. One star in particular, designated S2, traces a complete elliptical orbit around an unseen point with a period of roughly 16 years. Its orbit is not gentle. At its closest approach, S2 sweeps within roughly 120 astronomical units of the central object, a distance comparable to the outer reaches of our own solar system. And at that point, it is traveling at more than 2.5% of the speed of light. That means it is moving at roughly 7,600 kilometers per second, fast enough to cross the entire diameter of our planet in less than 2 seconds. The precision of this orbit and the orbits of dozens of other stars tracked nearby allowed both teams to calculate the mass of the invisible object they were all circling. The result converged with remarkable consistency on a figure of approximately 4 million solar masses, concentrated into a region so compact that no known object other than a black hole could account for it. For this work, Genzel and Ghez shared the Nobel Prize in Physics in 2020, alongside Roger Penrose, who had demonstrated decades earlier that the formation of black holes is a robust prediction of general relativity. Their achievement was not merely the confirmation of a black hole. It was the demonstration that patient, careful observation, watching stars move across the sky year after year, point by point, could weigh the invisible heart of a galaxy. In May of 2022, a further confirmation arrived from an entirely different direction: the Event Horizon Telescope. Not a single instrument, but a global network of radio dishes spread across continents, linked together to function as a single Earth-sized observatory, released an image of Sagittarius A star itself. The image showed a bright, slightly uneven ring of radio emission surrounding a dark central shadow. That ring is light from superheated gas orbiting just outside the event horizon, material moving so fast and glowing so intensely that it becomes visible even across 26,000 light-years of intervening space. The dark center, the shadow, marks the region from which no light escapes. It was only the second time a black hole had been imaged in this way. The first was the supermassive black hole at the center of the galaxy M87, captured 3 years earlier by the same collaboration. But to see the shadow of our own galaxy's central black hole, to know that it is there not through inference alone, but through a direct portrait assembled from radio light gathered by telescopes on every continent, was something that carried a quieter and more personal weight. This is not a distant object in a foreign galaxy. This is the center of our home, and we have seen it. Despite its tremendous mass, Sagittarius A star is astonishingly quiet. It is what astronomers might call an underluminous black hole, an object that accretes matter at a rate far below what it could theoretically consume. In many other galaxies, the central supermassive black hole is surrounded by an accretion disk, a vast swirling reservoir of gas spiraling inward at tremendous speeds, heating through friction until it glows with a ferocity that can outshine every star in its host galaxy combined. These blazing cores, known as active galactic nuclei, are among the most luminous objects in the observable universe. They can launch jets of energized particles at nearly the speed of light, punching outward for hundreds of thousands of light years beyond the galaxy itself. They can heat surrounding gas so thoroughly that star formation across entire regions is suppressed. They are engines of extraordinary violence and power. But Sagittarius A star does none of this. It consumes only a tiny trickle of the gas that drifts near it. the energy it radiates is a vanishingly small fraction of what it could produce if it were feeding more actively. If you could somehow observe it from a few light years away, you would not see a furnace. You would see quiet. A gravitational presence felt through the motion of everything around it, but otherwise restrained, almost withdrawn, as if the most powerful object in the galaxy had found its rest. Even its flickering, the small, irregular variations in brightness that radio and infrared telescopes detect from time to time, is modest, the faint pulse of a system at ease with itself, rather than in turmoil. This calm is not unique to our galaxy. Supermassive black holes are now understood to be a common, perhaps universal, feature of large galaxies throughout the cosmos. Nearly every large galaxy that has been examined with sufficient care appears to harbor one at its center. Their masses vary enormously, from a few million solar masses, like ours, to billions of solar masses in the most massive galaxies. But their presence is remarkably consistent. The era of peak black hole activity, when active galactic nuclei blazed most fiercely across the universe, occurred billions of years ago, when galaxies were still assembling, and gas was more readily available near their centers. As galaxies matured and their central gas supplies were consumed, expelled, or settled into stable configurations, many of their black holes entered quieter phases. Sagittarius A star may have been more vigorous in the past. There are hints, faint echoes of X-ray light reflecting off molecular clouds near the center, suggesting that a more luminous outburst may have occurred a few hundred years ago. A brief flare in the long calm. But today, the black hole rests, and the galaxy turns around it as it has for billions of years, gently and without interruption. Surrounding Sagittarius A star and the nuclear star cluster is a broader region that astronomers call the Central Molecular Zone, a vast reservoir of dense molecular gas stretching across several hundred light-years near the galactic center. This zone holds enormous clouds of hydrogen, carbon monoxide, and other molecules, containing a significant fraction of the galaxy's total supply of dense gas. The clouds here are warmer, denser, and more turbulent than the molecular clouds found in the spiral arms farther out. Some are among the most massive concentrations of gas anywhere in the Milky Way. Individual clouds containing millions of times the mass of the Sun. And yet, despite this abundance of raw material, the Central Molecular Zone forms new stars at a rate far lower than its mass alone would predict. By the standards of the outer galaxy, where clouds of similar density and mass would be vigorously producing new stars, the center seems restrained, as if something is holding the process back. The extreme turbulence of the region likely plays a role, preventing gas from settling into the quiet collapse that star formation requires. The powerful tidal forces near the center also contribute, shearing clouds before they can condense. And the intense magnetic fields that pervade the inner galaxy may add a stabilizing pressure that further resists collapse. The result is a paradox of abundance, a place overflowing with the ingredients of creation, yet creating far less than it could. It is as though the center of the galaxy is holding its breath, keeping vast reserves in waiting, neither consuming them nor releasing them, balanced in a state of patient tension. Threading through this region are structures that give the inner galaxy a character unlike anything found in the disk where we live. Enormous filaments of magnetized gas stretch for tens of light years, aligned roughly perpendicular to the galactic plane, glowing faintly at radio wavelengths like luminous threads drawn through the darkness. These magnetic filaments were first discovered in the 1980s, and their origin remains a subject of active research. They appear to trace powerful magnetic fields near the galactic center, fields far stronger than those found in our local stretch of the disk. And they give the inner galaxy an almost architectural quality, as though invisible scaffolding has been erected around the core, shaping the movement of gas and charged particles along ordered pathways. More recent radio surveys have revealed hundreds of these filaments, some grouped into bundles, others arranged in patterns that suggest a large-scale magnetic order pervading the region. The galactic center is not merely a gravitational well. It is also a magnetic landscape, sculpted by forces that the eye cannot see, but that are powerful enough to direct the flow of matter across vast distances. Gas does not simply fall inward here. It follows channels, traces lines of force, and settles into configurations dictated by the interplay of gravity, rotation, and magnetism. The result is a region of startling complexity and of startling beauty, if you could see it in the wavelengths that reveal its full character. Extending far above and below the galactic plane, stretching outward from the center in both directions, are two colossal structures known as the Fermi bubbles. These are enormous lobes of high-energy gas, each one reaching roughly 25,000 light-years above and below the disk, a span comparable to the distance from the center to our own Sun. They were discovered in 2010 using data from the Fermi Gamma-Ray Space Telescope, and their scale is staggering. Together, the two bubbles stretch across roughly half the diameter of the entire galaxy, billowing outward from the center like the exhaled breath of something immense. The exact mechanism that produced them is still debated. They may have been inflated by a period of more intense feeding by Sagittarius A star in the relatively recent past, when a larger volume of gas drifted close enough to be captured and heated. Or they may have been driven outward by a concentrated burst of star formation near the galactic center, where the combined winds and explosions of many massive stars could have launched enormous outflows of hot gas perpendicular to the disk. Either way, the bubbles are evidence that the center of the galaxy has not always been as quiet as it appears tonight. Something, at some point in the cosmic recent past, released an extraordinary amount of energy, enough to push heated material tens of thousands of light-years above and below the plane of the galaxy. The bubbles are fading now, their edges grow cooler, their glow softens. They are remnants of a louder era, echoes of a time when the galactic center spoke more forcefully than it does in the present epoch. And their gradual dimming is itself a kind of settling, the galaxy exhaling and growing still again, returning to the quiet that seems to be its natural state. The galactic center, taken as a whole, is a place of profound contrasts held together in balance. It contains the oldest stars in the inner galaxy, alongside young ones, whose presence defies expectation. It harbors the most massive single object in the Milky Way, 4 million solar masses of invisible gravitational authority. Yet that object sits in near silence, barely consuming, barely radiating, a cosmic anchor wrapped in calm. It holds vast reserves of dense molecular gas, enough to build millions of stars, and yet that gas forms stars at a fraction of the expected rate, as though the center prefers patience to haste. Its magnetic fields are powerful and far-reaching. Its past outbursts are visible in structures that span the galaxy. And yet, the present moment, the moment we are in right now, is one of deep and settled quiet. This is not the kind of center you might expect from stories of cosmic drama. No blazing maelstrom, no relentless engine of destruction. It is something more interesting than that. It is a place where the most extreme conditions in the galaxy have found their way to equilibrium, where immense forces have arranged themselves into order, and where the boundary between power and stillness has dissolved into something like peace. There is comfort in that, if you let it settle. If a black hole 4 million times the mass of our sun can sit at the center of everything and simply hold the galaxy together, not consuming it, not tearing it apart, but anchoring it with invisible steadiness, then perhaps calm is not the absence of intensity. Perhaps it is what intensity becomes when it has nothing left to prove. The stars near the center continue their orbits, tracing elegant curves that have been tracked, measured, and predicted with extraordinary care. The gas drifts in its patterns. The magnetic filaments hold their shape. And Sagittarius A star remains where it has been since the galaxy assumed its present form. Centered, patient, and profoundly still. You do not need to hold any of this in your mind tonight. Let the details soften into impressions. Let the numbers and the names drift into the background like stars dimming at the edge of vision. What remains is simple. The galaxy has a heart. That heart is calm, and far from its luminous center, in a quiet arm, on a small and gentle world, you are resting safely within the structure it holds together. Let that be enough for now. Let your breath slow a little further. Let the stillness of the galactic center become, for just a moment, your own. The Milky Way is old. Not old in the way a cathedral is old, or a mountain, or even the rocks beneath the deepest sea. It is old on a scale that makes the entire history of the Earth feel like the last few seconds before midnight. The galaxy began assembling itself more than 13 billion years ago, in an era when the universe was still in its infancy, when the cosmic background radiation had only recently released its hold on matter, and the first structures of any kind were just beginning to gather from the faint, nearly uniform sea of hydrogen and helium that filled all of space. The universe at that time was dark. No stars had yet ignited. No galaxies had yet taken shape. It was only gas, vast cooling clouds of it, drifting through an expanding cosmos that had not yet learned what it could become. And then, slowly, guided by the quiet pull of gravity, the densest regions of that gas began to draw together. The story of the Milky Way begins there, in that darkness, in the gathering of the first light. The oldest stars in our galaxy are survivors of that earliest era. They live primarily in the galactic halo, the great spherical envelope of sparse, ancient stars and globular clusters that surrounds the disk. And their ages place them within a few 100 million years of the Big Bang itself. Some of them have been burning for more than 13 billion years, which means they ignited before the Milky Way had anything resembling its present shape. When these stars first began to shine, the galaxy was not a graceful spiral. It was a loose, irregular assembly of small gas clouds and proto-galactic fragments, still merging, still collapsing, still searching for the form it would eventually find. These ancient halo stars carry that history in their chemistry. They are made almost entirely of hydrogen and helium, the elements that existed before any star had lived long enough to forge heavier ones and scatter them into space. Astronomers describe them as metal poor, using the word metal in a specialized sense that includes every element heavier than helium. Carbon, oxygen, iron, silicon, all of the building blocks that would later make rocky planets and complex chemistry possible, are present in these old stars at only the faintest trace levels, sometimes hundreds or even thousands of times less abundant than in the Sun. Their poverty is not a failing, it is a timestamp. It tells us that these stars formed from nearly pristine material, gas that had not yet been enriched by the deaths of earlier generations. They are witnesses to the universe's chemical dawn. One of the most celebrated of these ancient stars is a subgiant in the galactic halo, catalogued under a designation so cumbersome that astronomers have given it a gentler nickname, the Methuselah star. It is close enough to study in remarkable detail, and its composition reveals an almost complete absence of the heavier elements that younger stars possess in abundance. For years, age estimates for this star produced a figure that seemed paradoxical, older than the universe itself by a narrow margin. That apparent contradiction was resolved not by discarding the star's age, but by refining the measurements on both sides. The age of the universe, determined from the cosmic microwave background and the expansion rate of space, settled at approximately 13.8 billion years. The star's age, once its distance and composition were measured more precisely, settled at roughly 13 billion years. Ancient beyond comprehension, but comfortably younger than the cosmos that contains it. What makes the Methuselah star so moving is not merely its age, but what that age implies. This star was already shining when the Milky Way was little more than a loose collection of gas and small clumps of matter. It watched the galaxy form around it. And it is still shining now, steady and quiet, a light that has persisted across nearly the entire history of the universe. Stars like this one are rare, but they are not alone. Surveys of the galactic halo have identified hundreds of extremely metal-poor stars, objects whose chemical compositions place their births in the first billion years of cosmic time. Some contain so little iron relative to hydrogen that they must have formed from gas, enriched by only a single previous generation of stars, or perhaps none at all. The very first stars that ever existed. The generation that astronomers call Population 3, are thought to have formed from gas that contained no metals whatsoever. Only the hydrogen and helium produced in the Big Bang. No confirmed Population 3 star has ever been observed. They are believed to have been massive, luminous, and short-lived, burning through their fuel quickly and dying in violent explosions that seeded the surrounding gas with the first crop of heavier elements. The most metal-poor stars we do observe, sometimes called Population 2 stars, likely formed from gas that had been touched by those first explosions, enriched just enough to carry the faintest chemical fingerprint of the generation that came before. Finding and studying these stars is a form of archaeology, except the artifacts are not buried in the ground. They are burning in the sky, still visible after 13 billion years. carrying the chemical memory of events that no telescope could ever directly observe. Globular clusters are among the most beautiful relics of this ancient era. Each one is a dense, spherical gathering of stars, typically a few 100,000 of them, sometimes more, held together by their mutual gravity into a compact, glittering ball. The Milky Way is known to host more than 150 of these clusters, and most of them are extraordinarily old. Many formed within the first 1 or 2 billion years of the galaxy's existence, and their stars share the same metal-poor chemistry as the ancient halo field stars, confirming that they belong to the same early chapter. A globular cluster is born all at once, or nearly so. A single burst of star formation from one vast cloud of gas, producing a population of stars that share the same age and the same initial composition. That simultaneous birth makes them invaluable to astronomers, because it means any differences between the stars within a cluster must be due to differences in mass, not in age or origin. By studying how the stars in a globular cluster have aged, which ones have already exhausted their fuel and evolved into red giants, which ones remain on the main sequence, and where the transition between the two falls, astronomers can estimate the cluster's age with impressive precision. Some globular clusters are among the most precisely dated objects in the galaxy. To observe one through a telescope is an experience of quiet astonishment. At low magnification, a globular cluster appears as a soft, hazy patch of light, almost cloud-like. As the magnification increases, the haze resolves into thousands of individual stars, packed so closely near the center that they seem to merge into a solid core of light, then gradually thinning outward into a delicate fringe of scattered points. The cluster Omega Centauri, the largest and brightest globular visible from Earth, contains roughly 10 million stars and spans a volume of space about 150 light-years across. 47 Tucanae, nearly as impressive, glows with a warm golden light that reflects the aged population of stars within it. Messier 4, one of the nearest globulars to us, is close enough that individual stars can be resolved even in modest amateur instruments. These clusters orbit the Milky Way on long, looping paths that carry them far above and below the galactic plane, plunging through the disk and swinging outward again in journeys that take hundreds of millions of years to complete. Their orbits are not circular. They are elongated and tilted at various angles, as though each cluster was flung into its path by the chaotic dynamics of the galaxy's early assembly. And in a sense, many of them were. Some globular clusters may not have been born within the Milky Way at all. They may have formed inside smaller galaxies that were later captured and absorbed by our own, their clusters surviving the merger, even as their parent galaxies were torn apart. This brings us to one of the most remarkable discoveries about the Milky Way's past. The galaxy did not form as a single, isolated event. It grew through the gradual accumulation and merger of smaller systems. Dwarf galaxies, proto-galactic fragments, and streams of gas that fell inward over billions of years. The evidence for this assembly history is written across the halo in the form of stellar streams, long, thin rivers of stars that trace the paths of galaxies the Milky Way has consumed. When a small galaxy falls into the gravitational embrace of a much larger one, it does not simply vanish. It is stretched, and pulled by tidal forces, its stars drawn out into an elongated arc that can wrap partway or even entirely around the host galaxy. These streams persist for billions of years, slowly dispersing but retaining enough coherence to be identified through careful observation. Their stars share common motions and common chemistry, distinguishing them from the general population of the halo, like a thread of one color woven through a tapestry of another. One of the most significant of these ancient mergers involved a galaxy that astronomers have named Gaia Enceladus, after the spacecraft that revealed its traces and the mythological giant who challenged the gods. This was no minor encounter. Gaia Enceladus was a substantial galaxy in its own right, and its collision with the early Milky Way, roughly 10 billion years ago, was a defining event in our galaxy's history. The merger delivered a large population of stars into the halo, many of which can still be identified today through their distinct chemical signatures and their orbital characteristics. They move on paths that are more eccentric and more randomly oriented than the orderly circular orbits of the disk. The collision may also have thickened the early galactic disk, scattering stars that had been moving in relatively flat orbits into higher, more inclined trajectories, contributing to what astronomers now identify as the thick disk. In a sense, the galaxy we live in was partly built by something it swallowed. The Milky Way is not a pristine creation. It is a composite, assembled from many sources, and the fingerprints of those ancient contributions are still legible to anyone who knows how to read them. Other mergers have left their own marks. The Sagittarius dwarf elliptical galaxy, a small companion currently being torn apart by the Milky Way's gravity, has been orbiting and shedding stars for billions of years. Its stellar stream wraps around the galaxy in an enormous loop, and pieces of it have been identified in surveys of the halo. The Magellanic Clouds, the large and small, are themselves satellite galaxies that interact gravitationally with the Milky Way and may one day be absorbed into it. The galaxy is not a static thing. It is still growing, still accreting material, still incorporating the debris of its gravitational conquests. The process is slow and overwhelmingly gentle by any human standard, unfolding across timescales that make the rise and fall of civilizations seem like the flicker of a candle. But it is ongoing. The Milky Way has eaten before, and it will eat again. But the era of frequent transformative mergers did eventually pass. The largest encounters, the ones capable of reshaping the galaxy's structure in fundamental ways, occurred primarily in the first few billion years. When the universe was denser and smaller, proto-galaxies were more likely to cross one another's paths. As the Milky Way grew larger and the surrounding neighborhood of small galaxies was gradually depleted through accretion, the pace of significant mergers slowed. The galaxy began to settle. Gas that had been stirred and heated by collisions radiated its energy away, cooled, and drifted inward toward the midplane. Slowly, over hundreds of millions of years, it organized itself into a thinner, flatter, more orderly rotating disk. The structure that would eventually become the thin disk we inhabit today. Stars born during and immediately after the last major disturbances retained the wider, more inclined orbits of that turbulent period, and those same stars form the thick disk that astronomers still observe surrounding the thinner, younger layer. But the new gas, arriving fresh and undisturbed, had no memory of the old violence. It settled into circular orbits, cooled further, and began forming stars in the calm, flat plain that would become the galaxy's primary site of creation for the next 8 or 9 billion years. This settling was not a single event with a clear beginning and end. It was a gradual transition, a long exhale after a period of upheaval. The galaxy did not decide to become orderly. It simply ran out of reasons to be chaotic. As the mergers faded and the gas cooled, the natural tendency of rotating material to flatten into a disk asserted itself, and the Milky Way found the shape it would carry forward into the present. The spiral arms emerged within this settled disk, maintained by the density waves that still ripple through it today. The bar took form as stellar orbits near the center responded to the evolving mass distribution, and the quiet, stable corridor where our sun would one day ignite became possible. Not because the galaxy was always calm, but because it had lived through its restlessness and come out the other side. The stillness of the disk is not a given. It is an achievement earned across billions of years of gradual cooling, gradual flattening, and the slow, patient work of gravity organizing matter into something that could endure. The history of the galaxy can be read not only in the spatial arrangement of stars, but in their chemistry. This field, sometimes called galactic archaeology, uses the detailed composition of individual stars as a record of the conditions under which they formed. The principle is straightforward. A star is born from a cloud of gas, and it incorporates whatever elements that cloud contains. As the star shines, it fuses lighter elements into heavier ones in its core. When it dies, through gentle shedding of its outer layers, or through the catastrophic violence of a supernova, it returns material to the interstellar medium, now enriched with elements that did not exist in the gas from which it formed. The next generation of stars forms from this enriched material, inheriting a slightly more complex chemical toolkit. Over billions of years, this cycle of enrichment builds up the abundance of heavy elements in the galaxy's gas, and each new generation of stars carries a more complete set of ingredients. Astronomers trace this progression by measuring the relative abundances of elements in stars of different ages and locations. A star in the halo with almost no iron formed early, from nearly pristine gas. A star in the disk with an iron abundance similar to the Sun formed later, from gas that had been processed through many cycles. The chemical evolution of the galaxy unfolds like a story told in elements, each one a character whose appearance signals a particular stage in the plot. Different elements are produced by different processes, and their relative abundances carry specific information. The alpha elements, oxygen, magnesium, silicon, calcium, and a few others, are forged primarily in the cores of massive stars, which live fast and die young as supernovae. Iron, by contrast, is produced in significant quantities by a different type of explosion. The thermonuclear destruction of white dwarf stars in binary systems, which occurs on a longer timescale. That difference in timing means that the ratio of alpha elements to iron in a star's atmosphere acts as a kind of clock. Stars that formed early, before the slower iron-producing channel had time to contribute significantly, tend to be enhanced in alpha elements relative to iron. Stars that formed later, after both channels had been running for a long time, tend to show a more balanced ratio. By plotting the alpha to iron ratio against overall metallicity for large samples of stars, astronomers can reconstruct the enrichment history of the galaxy in remarkable detail, separating populations that formed quickly from those that formed gradually, and distinguishing stars born in the Milky Way from those accreted from smaller satellite galaxies, whose enrichment histories followed different paths. This chemical storytelling extends even to individual elements that serve as tracers of particular events. The presence of europium and other heavy elements formed through the rapid neutron capture process, a violent nucleosynthetic pathway that occurs in neutron star mergers and possibly in certain supernovae, reveals that the galaxy experienced these extreme events early enough for their products to be incorporated into some of the oldest surviving stars. The detection of lithium, a fragile element destroyed easily inside stars, provides a different kind of constraint, linking stellar observations to the conditions of the Big Bang itself, when a small but measurable amount of lithium was produced alongside hydrogen and helium. Each element is a word in a language that astronomers are still learning to read fluently, and every new survey that measures the compositions of thousands or millions of stars adds new sentences to the narrative. The Milky Way is not merely old, it is articulate. Its history is recorded in the very atoms of which its stars are made. Our own sun is a product of this long enrichment. It formed roughly 4.5 billion years ago from a cloud of gas in the galactic disk that had been cycled through many previous generations of star formation and stellar death. By the time the sun's birth cloud collapsed, it contained a rich assortment of heavy elements: carbon, nitrogen, oxygen, silicon, iron, and dozens of others, accumulated over more than 8 billion years of galactic chemical evolution. Those elements did not remain only in the star. They also condensed into the disk of dust and gas that surrounded the young sun, and from that disk the planets formed. The iron in the Earth's core, the oxygen in its atmosphere, the carbon in every living cell, all of these were forged inside earlier stars, scattered into space through their deaths, mixed into the interstellar medium, and gathered together again when our own corner of the galaxy collapsed into a new solar system. The Sun is not a first-generation star. It is not even close. It is a late arrival, born into a galaxy that had already spent billions of years preparing the ingredients it would need. And those ingredients, built up patiently through cycle after cycle of stellar birth and death, are what made a rocky, water-bearing, life-supporting world possible. The chemistry of the Earth is the chemistry of the galaxy's patience. The age of the Milky Way is difficult to state as a single number, because the galaxy did not spring into existence at one instant. Its oldest components, the ancient halo stars, the first globular clusters, date back more than 13 billion years. Its disk is younger, having formed and settled over a more extended period, and parts of the disk are still being built today as gas cools and new stars ignite. The thick disk may have formed more than 10 billion years ago, while the thin disk, where most active star formation now occurs, developed more gradually and continues to evolve. In a sense, the galaxy has no single birthday. It has a history of becoming, a long, layered process of accumulation, enrichment, and settling that stretched across the majority of cosmic time. The spiral structure we observe now is not a relic of the galaxy's birth. It is a relatively recent feature, maintained by the dynamics of the rotating disk and the density waves that pass through it. And it may have looked quite different at various points in the past. The Milky Way of 5 billion years ago was already ancient, but it was not the same galaxy it is today. And the Milky Way of 5 billion years from now will be different again, reshaped by the ongoing flow of gas, the gradual migration of stars, and the eventual merger with the Andromeda Galaxy, which is approaching from across the local group at a pace that will not bring the two together for several billion years yet. There is something profoundly calming about this depth of time. The numbers themselves resist comprehension. 13 billion years is not a quantity the human mind was built to feel, but the principle behind them carries a kind of emotional weight that the numbers alone cannot express. The galaxy has been here for nearly the entire history of the universe. It was assembling itself when the cosmos was less than 1 billion years old. It watched the first heavy elements appear, the first dust grains condense, the first rocky bodies gather from the debris of dying stars. It was already old when the sun ignited. It was already ancient when the first living cell divided on the surface of a young, warm Earth. And it has continued turning steadily and without interruption through every moment of every era that has followed. The ice ages, the extinction events, the emergence and disappearance of entire lineages of life, all of these have unfolded within a galaxy that barely noticed, that carried its world gently through space without comment, without pause, without the slightest falter in its long, slow rotation. The oldest globular clusters have orbited the galaxy dozens of times since they formed. The halo stars have traced their elongated paths through the galaxy for so many revolutions that the number defies useful visualization. And the disk, young by comparison, has still been turning for long enough that the halo stars have been circling the galaxy since before most of its present structure existed. They predate the disk. They predate the spiral arms. They predate the bar and the thin, calm plane where the sun would one day form. Some of them were already billions of years old when the first rocky planets began to condense from enriched gas in the galactic disk. Their light has been steady through every era, through the age of heavy bombardment, through the long rise of oxygen in Earth's atmosphere, through the appearance and disappearance of entire kingdoms of life. They noticed none of it. They simply continued on their long orbits, patient and unhurried, carrying the chemistry of the early universe through a galaxy that kept changing around them. Their patience is the galaxy's patience, the patience of a system that builds itself slowly, enriches itself gradually, and carries everything it has ever made along for the ride. That patience extends to what the galaxy has become. The Milky Way tonight is the sum of everything that came before. Every merger, every supernova, every long cycle of enrichment and collapse. The heavy elements in the spiral arms were assembled by countless generations of stars, each one contributing a small addition to the chemical inventory before passing its material on. The structure of the disk was shaped by the interplay of gravity, angular momentum, and the slow accumulation of gas over billions of years. The halo preserves the memory of the galaxy's turbulent youth, when mergers were frequent and order had not yet been established. And threading through all of it, connecting the earliest epochs to the present moment, is the continuous flow of matter from old stars to new. A river of atoms that has been running since the galaxy first began to form, and that will continue to run for as long as stars continue to be born. You are part of that flow. The calcium in your bones was forged in a star that died before the sun existed. The iron in your blood passed through at least one supernova, and possibly several, before it settled into the cloud of gas that would become our solar system. The oxygen you are breathing right now was built inside a massive star somewhere in the galactic disk, expelled into space when that star reached the end of its life, and mixed into the interstellar medium, where it drifted for millions of years before being swept up into the collapsing cloud that formed the sun and its planets. You are not separate from the galaxy's history. You are made of it. Your body is a library of elements whose origins span billions of years and whose journeys have crisscrossed the galaxy many times over. When you breathe, you are completing a cycle that began in the cores of ancient stars. When you rest, you are resting inside a structure that has been preparing the conditions for your existence since long before the Earth was formed. Let that thought settle like something warm. The galaxy is old, and its age is not something to fear. It is a depth of time so vast that it absorbs worry the way the ocean absorbs rain, not by resisting it, but by being so much larger that the disturbance simply dissolves. Whatever you carried into this evening, whatever was pressing against your thoughts when you first lay down, exists within a galaxy that has been turning for 13 billion years without urgency and without haste. The stars that were old when the Earth was young are still shining. The clusters that formed in the galaxy's infancy are still orbiting, still intact, still carrying the chemistry of the early universe in their ancient light. And the disk that holds your world continues its slow revolution as it has for longer than any mind can truly fathom. Nothing about this night is rushed. Nothing about this galaxy has ever been rushed. It simply continues, patient and immense, carrying its history forward into a future that extends beyond any horizon you could name. Let that continuity hold you for a while. Let the age of the galaxy become a kind of permission. Permission to rest, to let go, to trust that the long, slow rhythm of things will carry you through, just as it has carried everything else since the very first star began to shine. The Milky Way is not finished. This is easy to forget, because the galaxy feels so vast and so ancient that it seems like something already completed, a monument to a creative era long past. But right now, as you lie here listening, new stars are being born inside the galaxy, not in some abstract, theoretical sense, but physically. Clouds of gas are collapsing, temperatures are rising, and in dense, hidden nurseries scattered along the spiral arms, new points of light are preparing to ignite for the very first time. The Milky Way is still building. It has been building for more than 13 billion years, and it has not stopped. The materials are different now, richer, more complex, laced with heavy elements forged by countless earlier generations of stars. But the fundamental process is the same one that has been running since the galaxy's earliest days. Gravity gathers gas. The gas grows dense, and somewhere in that density, a star is born. Star formation in the Milky Way today is concentrated primarily in the spiral arms, in vast structures known as molecular clouds. These are enormous reservoirs of cold, dense gas. mostly molecular hydrogen, along with smaller amounts of carbon monoxide, dust, and traces of more complex molecules that can stretch across tens or even hundreds of light years. They are among the coldest places in the galaxy, with internal temperatures often hovering only a few tens of degrees above absolute zero. That extreme cold is not incidental, it is essential. For a cloud of gas to collapse under its own gravity and form stars, it must be cold enough that its internal pressure cannot resist the inward pull. Warm gas pushes outward. It resists compression. Cold gas surrenders to gravity more easily, allowing dense pockets to contract, fragment, and eventually reach the temperatures and pressures needed to sustain nuclear fusion. The coldest, darkest places in the galaxy are, paradoxically, where new light is born. Inside these molecular clouds, the process of star formation unfolds in stages that can take millions of years. A region of slightly higher density begins to attract surrounding material. As it gathers mass, its gravitational pull strengthens, drawing in more gas and dust from the cloud around it. The collapsing region heats as it contracts. Gravitational energy converts to thermal energy. And at its center, a dense, hot core begins to form. This protostar is not yet a true star. It does not yet sustain nuclear fusion, but it is growing, still pulling in material from a surrounding disk and envelope, glowing with the warmth of compression. Over time, as the core grows denser and hotter, it reaches a threshold, roughly 10 million degrees, at which hydrogen nuclei begin to fuse into helium. At that moment, a star is born. The outward pressure of nuclear energy balances the inward pull of gravity, and the object settles into a long, stable equilibrium that can last for millions, billions, or even trillions of years, depending on the star's mass. The largest, most massive stars burn through their fuel in just a few million years, blazing with extraordinary luminosity before dying in supernovae. The smallest, coolest red dwarfs can burn so slowly that none of them, not a single one that has ever formed in the entire history of the universe, has yet had time to exhaust its fuel. They are all still shining, every one patient and dim and nearly eternal. The most famous of the galaxy's stellar nurseries is the Orion Nebula, a glowing cloud of gas and dust visible to the naked eye as a faint, fuzzy patch in the sword of Orion. Through a telescope, it reveals itself as a landscape of extraordinary beauty. Luminous curtains of ionized hydrogen glowing pink and red. Dark pillars of denser gas silhouetted against the light. And at the center, a small cluster of young, hot stars whose intense radiation illuminates the entire region. The Orion Nebula lies roughly 1,340 light-years from Earth, making it one of the nearest large star-forming regions, and it has been studied in more detail than almost any other nebula in the sky. Within it, astronomers have identified protostars still embedded in their birth cocoons. Disks of dust and gas around young stars that may one day form planetary systems, and jets of material streaming outward from newborn stars at hundreds of kilometers per second, punching through the surrounding cloud like narrow beams of light cutting through fog. It is a place of active creation, messy, luminous, and alive, and it is happening right now in our own galaxy, a relatively short distance from where we sit. But the Orion Nebula is only one of many. The Carina Nebula, far larger and more distant, hosts some of the most massive and luminous stars known in the Milky Way, embedded in a vast complex of gas and dust that spans more than 300 light-years. The Eagle Nebula, famous for the towering columns of gas photographed by the Hubble Space Telescope and nicknamed the Pillars of Creation, is another active region where stars are forming within dense fingers of molecular material that are slowly being eroded by the radiation of nearby young stars. Across the galaxy, in every major spiral arm, similar regions exist, some enormous, some modest, all participating in the same slow, ongoing process of turning gas into stars. The Milky Way is estimated to form new stars at a rate of roughly 1 to 3 solar masses per year, a pace that sounds modest until you consider that it has been sustained, with variations for billions of years, and that each solar mass of new star formation represents the creation of something that will shine for an almost incomprehensible stretch of time. The galaxy builds slowly, but it never stops. The creation of new stars is not an isolated act. It is part of a cycle, a loop of cause and consequence that connects the death of one star to the birth of another across millions of years and hundreds of light years. When a massive star reaches the end of its life, the explosion that follows does more than scatter heavy elements into the surrounding gas. It sends a shockwave outward, an expanding shell of energy and heated material that plows into the interstellar medium like a ripple spreading across still water. Where that shell encounters a nearby molecular cloud, it compresses the gas along the cloud's edge, squeezing it into denser filaments and clumps. If those clumps reach a critical density, they begin to collapse under their own gravity, and the process that leads to a new star begins again. In this way, the death of one generation can trigger the birth of the next. Supernovae do not merely end a star's story. They can begin a dozen others. This feedback operates on timescales far longer than any human endeavor, but its effects are visible throughout the galaxy. Astronomers have identified regions where arcs and shells of expanding gas, the remnants of past explosions, border newly forming star clusters, the geometry itself suggesting a causal link. The great star-forming complexes of the spiral arms are not single, spontaneous events. They are often chains of creation, one burst of star formation, seeding the conditions for the next, each generation building on the debris of the one before. The Milky Way is not a factory that runs in one direction. It is a cycle, a slow, self-sustaining engine in which matter flows from gas to star, from star back to gas, and from gas to star again, enriched a little more each time. Nothing is wasted. Nothing is truly lost. The atoms that make up a dying star do not vanish. They return to the galaxy, drift through space for a while, and eventually find themselves inside something new. The galaxy recycles itself with a patience that borders on the infinite, and every new star is a product of everything that came before it. The space between the stars is not empty. It may look that way on a clear night, when the stars seem to float against a backdrop of pure darkness. But the darkness is filled with material, thin, widely scattered, but present everywhere. Astronomers call it the interstellar medium, and it occupies the vast volumes between stellar systems throughout the galactic disk. This medium is not uniform. It exists in several distinct phases, each defined by temperature and density, each occupying a different fraction of the galaxy's volume. The coldest phase consists of dense molecular clouds the vast nurseries where new stars are born, where temperatures hover near absolute zero and the gas is thick enough to block the light of background stars. These clouds fill only a small percentage of the disk's volume, but they contain a disproportionate share of its mass, because the gas within them is compressed into heavy, lightless reservoirs. Surrounding and between these cold pockets is a warmer phase of neutral hydrogen, gas that is not bound into molecules, but has not been heated to extreme temperatures. This warm, neutral medium fills a larger fraction of the disk and is the material most commonly traced by the 21-centimeter radio line that revealed the galaxy's spiral structure. Hotter still is a diffuse phase of ionized gas heated by the radiation of nearby stars or by the blast waves of distant supernovae, glowing faintly at wavelengths the eye cannot see, and filling the largest volume of all, threading through the gaps between everything else, is an extremely hot, extremely thin phase, sometimes called the coronal gas, heated to millions of degrees by the cumulative energy of supernova explosions. The local bubble itself is filled with this hot, rarefied gas, remnant warmth from the explosions that carved the cavity millions of years ago. These phases are not fixed. They flow into one another constantly. A supernova can heat cold gas into the hot phase in an instant. Over millions of years, that hot gas radiates its energy away and cools, eventually condensing back into the warm or cold phases from which new stars may one day form. The interstellar medium is a living weather system, not of rain and wind, but of heating and cooling, compression and expansion, cycling endlessly through states that sustain the galaxy's ongoing creation. Between the stars, where nothing seems to exist, everything is slowly becoming something else. And yet, for all the stars it has made, and all the gas it still contains, the Milky Way is held together by something it cannot see. This is one of the strangest and most humbling facts about our galaxy, and about the universe at large. The visible matter in the Milky Way, all the stars, all the gas, all the dust, all the planets and moons, and everything you could ever observe with any telescope at any wavelength, accounts for only a small fraction of the galaxy's total mass. The rest is something else, something that does not shine, does not absorb light, does not interact with electromagnetic radiation in any detectable way. It is present only through its gravitational influence, and that influence is enormous. Astronomers call it dark matter, and its existence was first suspected not through theory, but through observation. The quiet, patient kind of observation that notices when things do not behave the way they should. The story begins with rotation. Stars and gas in the Milky Way orbit the galactic center, just as planets orbit the sun. If the galaxy's mass were concentrated primarily in its visible center, in the dense bulge and the luminous inner disk, then the orbital speeds of stars in the outer regions should decrease with distance, just as the outer planets of our solar system orbit more slowly than the inner ones. This expectation is straightforward and well grounded in the physics of gravity. But when astronomers measured the actual rotation of the Milky Way and other spiral galaxies, they found something very different. The orbital speeds of stars and gas in the outer disk did not decline. They remained high, stubbornly, persistently high, far beyond the point where the visible mass could account for them. The outer regions of the galaxy are moving too fast to be held in orbit by the gravity of the matter we can see. Something else must be there, providing additional gravitational pull, extending far beyond the visible disk, massive enough to keep the outer stars bound to the galaxy, even at their unexpectedly high velocities. This discovery did not arrive in a single moment. The idea that galaxies might contain unseen mass was raised as early as the 1930s by the Swiss astronomer Fritz Zwicky, who noticed that galaxies in clusters were moving faster than the visible mass of those clusters could explain. But the most compelling evidence for dark matter in individual galaxies came from the work of the American astronomer Vera Rubin, who in the 1970s and 80s carefully measured the rotation curves of spiral galaxies, plotting how orbital speed changes with distance from the center, and found galaxy after galaxy the same pattern. The curves did not fall off. They stayed flat, and the only explanation consistent with the data was that each galaxy was embedded in a vast halo of unseen mass, a dark matter halo, extending far beyond the visible stars, providing the gravitational scaffolding that holds everything together. The Milky Way is no exception. Its dark matter halo is estimated to extend for hundreds of thousands of light years beyond the edge of the visible disk, encompassing a volume of space far larger than the galaxy you would see in any image. The total mass of this halo is thought to be roughly 10 to 20 times the mass of all the visible matter in the galaxy combined. That means the stars, the gas, the dust, everything that emits or reflects or absorbs light, accounts for perhaps 5 to 10% of the Milky Way's total gravitational budget. The rest is dark matter. We do not know what it is made of. Decades of experimental and theoretical work have narrowed the possibilities. It is almost certainly not composed of ordinary atoms, not made of failed stars or cold gas or wandering planets. But its fundamental nature remains one of the deepest open questions in all of physics. It does not emit light. It does not block light. It passes through ordinary matter almost without interaction. And yet without it, the galaxy as we know it could not exist. The stars in the outer disk would fly away. The spiral arms would unwind. The structure that holds your world in its quiet orbit would dissolve. Dark matter is the invisible architecture of the Milky Way, unseen, unfelt, and absolutely essential. There is something strangely peaceful about this. The galaxy you see on a clear night, that pale band of light, those familiar constellations, is only a fraction of what is actually there. Most of the Milky Way is invisible, not because it is hidden by dust or too faint to detect, but because it is made of something that does not interact with light at all. You are surrounded by it. You are, in a sense, immersed in it. And it asks nothing of you. It does not announce itself. It does not demand attention. It simply holds the galaxy together, quietly, and has done so for as long as the galaxy has existed. The largest component of your home is something you will never see and never touch, and yet it is the reason your home holds its shape. There is a lesson in that, if you want one. But there is also just the fact of it, gentle, strange, and deeply reassuring. While dark matter holds the galaxy in place, everything within it is in motion. Nothing in the Milky Way is still. The sun, the Earth, and every planet in the solar system are orbiting the center of the galaxy at a speed of roughly 800,000 kilometers per hour. At that velocity, You could circle the entire Earth in about 3 minutes, and yet you feel nothing. There's no wind, no vibration, no sense of movement at all, because everything around you, the air, the ground, the moon, the neighboring stars, is moving with you, carried along in the same vast current. The motion is real, but it is shared, and shared motion is indistinguishable from stillness. You are traveling through the galaxy at extraordinary speed, and you are completely, perfectly at rest. One complete orbit of the galactic center takes the solar system approximately 225 million years. Astronomers sometimes call this period a galactic year, and it is a unit of time so vast that it reframes the history of the Earth in humbling terms. The Earth is roughly 4.5 billion years old, which means it has completed only about 20 orbits of the galaxy in its entire existence. 1 galactic year ago, the earliest dinosaurs were just beginning to appear. 2 galactic years ago, the most complex life on land consisted of simple plants and arthropods. 4 galactic years ago, complex animal life had not yet appeared. The solar system has not been around the galaxy very many times, and each orbit has carried it through a slowly changing landscape. Different stretches of the spiral arms, different densities of interstellar gas, different neighborhoods of stars that come and go as the sun traces its long circular path. This motion is not only orbital. The solar system also bobs gently up and down through the plane of the galactic disk as it orbits, like a horse on a carousel, crossing above and below the midplane in a cycle that takes tens of millions of years. At times, the sun sits slightly above the disk. At other times, slightly below. These oscillations carry us through regions of varying stellar density and interstellar gas, and some researchers have explored whether they might correlate with patterns in the geological or biological history of the Earth. Periods of increased meteor impacts, perhaps, or fluctuations in cosmic ray exposure. The connections remain speculative, but the underlying motion is real. Your world is not fixed in one layer of the galaxy. It drifts gently through the disk's thickness, rising and falling in a rhythm far too slow for any human lifetime to notice, but written clearly in the equations that describe the gravitational structure of the Milky Way. The galaxy itself is also in motion, not only rotating, but traveling through space as a whole. The Milky Way is part of a small gathering of galaxies known as the Local Group, which includes our nearest large neighbor, the Andromeda Galaxy, along with the Triangulum Galaxy, and several dozen smaller dwarf galaxies scattered throughout the surrounding volume of space. The Local Group is bound together by gravity, its members orbiting a common center of mass located somewhere between the Milky Way and Andromeda. And within this group, the 2 largest galaxies, ours and Andromeda, are approaching each other. The gap between them is closing at a rate of roughly 110 kilometers per second, a speed that sounds alarming only if you forget the distance involved. Andromeda is currently about 2.5 million light-years away. At the present rate of approach, the 2 galaxies will not meet for another 4 to 5 billion years. The collision, when it eventually occurs, will be one of the most significant events in the Milky Way's future. But it is so far away in time that the Sun will have exhausted most of its fuel before the merger reaches its peak. When the 2 galaxies do finally meet, the encounter will not be the violent crash that the word collision might suggest. Galaxies are mostly empty space. The distances between individual stars are so immense that direct stellar collisions will be extraordinarily rare, even as the two galaxies pass through each other and eventually merge. What will change is the structure. The gravitational interaction will distort both galaxies, pulling out long tidal tails of stars and gas, scrambling the orderly rotation of their disks, and eventually blending them into a single, larger system. Over the course of hundreds of millions of years following the initial encounter, the two galaxies will settle into a new configuration. Most likely a large elliptical galaxy, rounder and less structured than either spiral was on its own. Astronomers have modeled this process in detailed computer simulations, and the results are both dramatic and strangely beautiful. Stars are flung outward in sweeping arcs. The spiral arms dissolve. New bursts of star formation erupt where gas clouds collide. And gradually, over a timescale that dwarfs human comprehension, the turbulence fades, and the merged system finds its equilibrium. Some astronomers have given this future galaxy a provisional name, Milky Way, a blend of its two parents, a name for something that does not yet exist, but that the laws of physics guarantee will one day come to be. And beyond even that merger, the story continues. Though it grows quieter as it goes, the merged galaxy will still contain gas, and for a time, new stars will continue to form. But the supply is not infinite. With each generation, more of the galaxy's hydrogen is locked inside long-lived stars or expelled into intergalactic space by the energy of stellar winds and explosions. The rate of star formation, already far below its ancient peak, will continue to decline. Over tens of billions of years, the galaxy will gradually exhaust the raw material it needs to build new suns, and the last stellar nurseries will close, not with any dramatic event, but with a slow fading, the way a fire dims when the last logs have been laid upon it, and no more are coming. What will remain are the longest-lived stars, the red dwarfs, those dim, patient embers that burn their fuel so slowly they can shine for trillions of years, long after the last massive star has exploded, long after the last sun-like star has swelled into a red giant and faded into a white dwarf. The red dwarfs will continue. They will glow faintly in a galaxy that has grown dark and still, carrying the last visible light through an era so long it dwarfs everything that came before. The galaxy will not die in any sudden sense. It will simply grow quieter, star by star, until the sky holds only the oldest, coolest, most enduring points of light, scattered across a structure that remembers, in its shape and its chemistry, everything it once was. And even then, the dark matter halo will remain, holding the remnants together in its invisible embrace, patient as it has always been. The galaxy's final chapter will not be written in fire. It will be written in the slow red glow of stars that refused to hurry, shining on into a silence so deep it becomes a kind of peace. But that future is unimaginably far away. It belongs to a time scale that no living mind needs to carry. Tonight, the Milky Way is here, whole and turning, carrying us with it in its slow and ancient revolution. The spiral arms wind outward through the disk. The molecular clouds drift and collapse and give birth to new stars. The old stars in the halo continue their long, looping orbits, carrying the chemistry of the early universe through the darkness. Dark matter holds the structure together, invisible and patient and everywhere. And at the center, Sagittarius A star sits in its deep quiet, anchoring the galaxy with a gravitational presence that shapes the motion of every star, every cloud, and every world within its reach. The Milky Way is not somewhere else. It is not a destination or a spectacle reserved for telescopes and observatories. It is the place where you already are. Every atom in your body was cycled through it. Every breath you take is composed of elements that were forged inside its stars. The ground beneath you is made of material that condensed from the same galactic cloud that formed the sun. And the water in your body has been part of this planet for billions of years, carried in a slow orbit around the galactic center the entire time. You have been orbiting the galaxy since before you were born, since before your species existed, since before the first creature drew breath on the surface of the Earth. The orbit does not require your attention or your effort. It simply continues, as it has for billions of years, steady and silent and sure. There is a version of this realization that feels overwhelming, a sense of scale so vast that it threatens to make everything small. But there is another version, a quieter one, that works in the opposite direction. The galaxy is enormous, and you are here inside it, not observing it from somewhere outside, not studying it from a distance, living in it, made of it, carried by it. The same gravity that shapes the spiral arms shaped the cloud that became your solar system. The same processes that built the iron in the galactic core built the iron in your blood. You are not a visitor to the Milky Way. You are one of its consequences. A brief, warm, conscious flicker in a structure that has been turning for longer than the Earth has existed, and that will continue turning long after every trace of this particular moment has been folded back into the galaxy's long memory. Tonight, the stars do not need you to count them. The spiral arms do not need you to trace their curves. The dark matter does not need you to understand it. And the slow orbit of your world around the galactic center will continue whether you are awake or asleep. There is nothing you need to hold on to. There is nowhere you need to go. The galaxy is carrying you, as it carries everything, in a motion so smooth and so encompassing that it feels like perfect stillness. Let your breathing settle into whatever rhythm feels most natural. Let the weight of the day dissolve into something older and wider than anything one day could contain. The Milky Way has been here for 13 billion years. It held the first stars. It held the gas that became the sun. It held the dust that became the earth. And tonight, it holds you. We did not choose to be born into this galaxy, on this particular world, under this particular scatter of stars. And yet here we are, part of a spiral 200,000 light years across, moving through space at extraordinary speed, completely still. The Milky Way has been turning for longer than the Earth has existed. Tonight it continues, quietly, carrying everything along with it. If you have enjoyed this journey, you can support Science into Sleep with a like, a subscription, or a quiet comment before you drift off. It helps more curious minds find these gentle evenings, and it keeps our nights of science and wonder going. But for now, you do not need to do anything at all. Let the galaxy hold you. Let the ancient light soften behind your eyes. Let your thoughts grow as quiet as the space between the stars. If you are still awake and would like one more journey, there'll be another waiting on the screen, ready to carry you onward. Otherwise, simply rest here, in the calm after the cosmos. Sleep well and good night.